All right. Good afternoon, everyone. Hello. So logistics-wise, couple things. Our next test, test 2, 2 weeks. Exactly 2 weeks from today. For good or for bad. That's what it is. I will start bringing in note cards hopefully next week. 5x8 note card. Same exact rules as the last test. You can bring a 5x8 note card with everyone and writing on it. I will provide the formula sheet. It will be the one that is uploaded currently. The formula sheet that I have uploaded currently is very, very slightly different than the last formula sheet I gave you all because I switched out harmonic motion for center of mass. So not a big deal, but if you want to just, it's still there. It's updated. If you look right here, this thing that looks gross, that's kind of new. And this looks worse than it is. Just trust me for now, it's not as bad as it looks. Okay? Yeah, that's good. Okay, so we'll get to that when we get to that. Okay? Center mass, we'll get to it real soon. So, hey, exam 2 weeks. There you go. The next thing is I made a document. I say I made a document. This one exists. I made it last semester, and I've updated it for Euro's class. This document is to help you evaluate your current/future grade in the class. I say current. Your future grade in the class. This document has every single assignment group that's in this class. Recitation activities, recitation attendance, clicker question total, adjusted quizzes, test 1 total, test 2 total, and the final. This document only works if every single red box is filled. So I will show you what I mean. Let's say you got 90% on the recitation activities, then the red goes away. Say attendance, you also have 90%. Woohoo. Clicker questions, you have a 95. Quizzes, maybe you have a 85. And test 1, maybe you got a 70. Behold, the final grade is absolutely terrible because it's not taken into account. You haven't put test 2 yet or the final in yet. So if you want to get an estimate of what your final grade in this class will be, basically this lets you determine what you need to get the grade you want. The reason I have sent this out, the reason this is posted is because the withdrawal deadline is this Friday. And so this is just a tool for those of you that wish to have this tool. If you're like, man, what do I need to do what do I need to score on the test and the final to actually get the grade I want? So you have to guesstimate your test 2. Let's say on test 2, you do the exact same. You get a 70. Again, it's not accounting for everything. Then the last thing is you got to put the score on your final. You got to guesstimate that. Let's say you do a bit better somehow, some way. You get an 80. Ta-da! There's your score in the course. Now, the reason I've made this document is twofold. Well, twofold. It's for 2 reasons. There's things in Canvas that there's things I do with the grades that I can't put in Canvas. Specifically, I calculate your all's grades with and without eye clickers. I calculate your grades with and without eye clickers. There's no way for me to show you that grade not in Canvas. This does this for you. It calculates the grade with and without eye clickers. And it takes the higher of the two. Behold, there's a grade with clickers. There's a grade without eye clickers. It takes the bigger one. What this also does is it determines whether or not the final will replace one of the tests. And if so, which one it will replace. So for example, let's change this to 75. If you score a 80, so your final will replace the lowest test score if it's higher. Only if it's higher. So in this case, if you want to see behind the scenes, if you hit the math tab, it does is the lowest test replaced? Yes. And it replaces the lowest test grade with an 80 and it does the math with that number. So you can see here, for example, right now it is being replaced because 80 is higher than these. If you score a 60 on the final and you go to the math tab, is the lowest test replaced? No. And then it shows that there. So anywho, it does the things that Canvas can't. There's things I do grading-wise for you all to your benefit that Canvas can't show, and this Excel document does those things. So, there you go. It exists. Use it or don't. It is for you to play around with. And again, you can kind of play around with it given your current grades and say, what do I need to do to get an A in the class? And you can just play with these numbers. Make that one a 90. Make this one an 80 or something. And it, changes things. Though, now that I just did that not change anything? I was wondering why that didn't change things. That is weird. All right, something is obviously broken here. I have to look at this. It is not working the way intended. I'm changing test 2 total, and it's not working, so I gotta look into this. Sadly, it seems to be slightly broken. Very sad. But I'm not going to spend the time figuring it out right now. It's mostly good, but it's a little bit off. All right. I'll play around with it later. Okay. I double-checked it, but clearly not enough. All right. We got 2 more momentum problems to do, and then we're going to jump into gravity. So nice and easy. All right. So here's a PowerPoint with a bunch of work on it. That's going to all go away. Review. Gone. All right. So recap. Last class. What did we talk about? Basically one equation. Where is it? Nope, not there. Not there. There it is. All right. This is the magic sauce, y'all. All conservation momentum problems are add up all your momentums in the beginning and then equal all your momentums at the end. This is how you do every single conservation momentum problem. How do you decide when to do a conservation momentum problem? If things hit each other. If there are collisions or inversely separations. That is how you decide whether or not you're going to do conservation momentum. So, we look at these problems. For example, this one, 2 figure skaters. Someone picks up someone. That's a collision. They interact with each other. Great, conservation momentum. A boy slides down a hill and he hits a boulder. That's a collision, conservation momentum. A falcon hits a bird. That's a collision, conservation momentum. The last problem we'll do today, a bunch of things, some deer are on a rock and then they jump off the rock. What happens? That's a separation, conservation momentum. All right? Okay, so let's do this one, y'all. A 0.9 kilogram falcon is diving at 28 meters per second on a downward angle of 35 degrees. It catches a 0.325 kilogram pigeon from behind. What is their combined velocity? They're hugging. Afterwards, if the pigeon's initial velocity was 7 meters per second, to the right. All right. First step is draw a picture. I drew the initial. You draw the final. What does my situation look like at the end? If you can't draw a picture of what the beginning and the end looks like, you're going to the rest of the problem falls apart. If you don't know physically what's happening, and that's true of momentum and energy, you need to know what it looks like. You don't need to have all the details, but you need to have a scene in your head. All right, so we got the falcon. It's going downwards. And we got the pigeon. It's going to the right. And at the end, they are attached to each other. And from this, you can have a pretty good approximation of which way they're going to go. If one's going down to the right and one's going to the right, the net result of this will be somewhere in between the two. It's okay if you can't quite draw which direction that arrow is going to go, but if you can, it helps out. It helps checking things. We'll call this V final. All right, so we write down our givens. We have mass 1, the mass of the falcon is 0.9 kilograms. We have mass 2, the mass of the pigeon, that's 0.325 kilograms. We have the magnitude of the velocity, the initial velocity, the magnitude of it, of the falcon. 28 meters per second. And immediately, the fact that we have a velocity at an angle means your mind should immediately recognize there's a step we're going to need to do, and we're just going to do that step now versus later. Remember, y'all, vectors. Vectors. You have to break them into their components. You have to break vectors into their components. If you ever see a vector at some angle, and it's not an energy problem, you need to break it into components. So, have fun. Go ahead and do it. Find the velocity of the falcon in the x. Find the velocity of the falcon in the y. Find the velocity of the pigeon in the x. Find the velocity of the pigeon in the y. Initial. Do it for yourself. And be very, 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 very careful. I can almost guarantee half of us are going to forget something on one of these givens. We'll see if you forget it. Yeah, what's up? Thank you. I appreciate the reminder. Oh, I'll tell you the one that my studio class got this morning. I recently went to the website conjunctivitis.com. It's a site for sore eyes. Conjunctivitis is something to do with sore eyes. I have no idea the medical details. Feel free to look it up. But there you go. Now you know what the word well, you kind of have a sense of what the conjunctivitis means. All right. So remember, y'all, when you're breaking things into vectors, you should draw a right triangle. So we look at our pigeon, and we draw this vector, this velocity vector, and we draw a triangle. And this is where I'm going to reveal the thing that many of you might have forgotten. When you break it into components, you need to draw arrows on those sides. They're not lines, they're arrows. So, which way does my y component point? Down. If you didn't realize that the y component's down, your entire answer to this problem will be wrong. You'll see why. And the x component points to the right. Now, the pigeon doesn't have a y component. I'm not going to draw a right triangle for the pigeon because it's already pointed to the right. So we'll just put the y component as 0. But yeah, when you do the x component of the falcon, that's going to be the adjacent side. Nope, the opposite side. So in this case, we're going to do 28 times sine of 35. For some reason I'm like, I was like, what am I doing? I was like, it should be cosine, but it should be cosine. I'm like, it's the opposite side of the hypotenuse, but that's nonsense. Why is it the cosine? Because it's the adjacent side of the angle. It's the side touching the angle. As I was saying it, I was like, something doesn't feel right here. All right, so it is cosine. And I'm going to just draw this a little nicer so you can read this in the future. All right, and this is the key. The y component is negative. If you don't put the y component as negative, your answers turn out wrong. When you work with vectors, the sign, whether it's positive or negative, comes from the picture. The sign of it comes from the picture. We're back in this, y'all. Energy was the only thing we've worked with so far where you didn't care. The sign you figure out from the math, not the picture. So, it's a very, very subtle thing, but it matters a lot. You will miss a question on the test if you don't realize that down is negative or to the left is negative when it comes to velocity vectors. We can't forget about that stuff. All right, and the x component of the pigeon is to the right. Step 2, what are we solving for? The final velocity, they are together. This is a conservation of momentum problem. It's a vector, so you got to do it for the x and for the y. So the sum of all momentums in the x equals the initial, equals the sum of all momentums final in the x. And the sum of all momentums in the y initial equals the sum of all momentums in the y final. I want you all to build these equations. I'm going to copy all this over to a new slide. But I want you all to build momentum and energy or build your own equations. That's how these work. Try it out. Build your own equations, y'all. And if you build the equation, you can test it by plugging in the numbers and doing all that. All right, so we look at the x direction and we say they start separated. So we get m1 v1 initial x. So I'll make this a little bit more clear here. In the x direction, you have m1 v1 initial x plus m2 v2 initial x equals, and they're together at the end. So it's m times v, but my new m, they're together. Together forever. Great. And then if you want to do the y component, it's the exact same thing, but I just replace it with y's. So m1 v1 initial y plus m2 v2 initial y equals m1 plus m2 v final y. Forgot to put x and y's at the end there. And ta-da, we built our equations, plug in the numbers, do the math. That's the last step. Now you do it. So, oh man, am I going to have room here? 0.9 times 22.4 plus 0.325 times 7 equals 0.9 plus 0.325 v final x. Totally fit. Ugh, that was sad. And then it's just an algebra problem. Plug that in your calculator. If you solve for v final x, you should get 18.7. If you did not get 18.7, something went wrong. I will double check it on my own calculator. So 0.9 times 22.4 plus 0.325 times 7 divided by the combined mass. Yay, we did it. Okay, I got like 18.31 for some reason. Did I write a number weird? Ah, there it is. Thank you. I wrote down a number wrong, and therefore it messed up my final thing. There we go. All right, I got 18.7. All right, so yeah, you just plug the whole left side in. That gives you 22.92 equals the right side, which is 1.225. You do some division and you get an answer of 18.7 meters per second. Repeat that for the other side. Repeat that for the y. Yeah. Yeah, I will tell you all what I want on the test. I know this problem did not say vector form. I actually put the answer in vector form for this. So on the problem set, this just says, give me the velocity. So it actually is the magnitude. I put it in vector form here because just to reinforce that whole x and y components. But we'll do the final step together as well. Through the magic of shrinking, I've given myself more room. Okay, then we do the y component, which is going to be 0.9 times negative 16.06 plus 0 equals 0.9 plus 0.325 times v final y. And you just plug that in your calculator. And you get v final y equals negative 11.79. Mine's kind of this. It's close enough to the answer I put here. Yay! All right, and if you want to find the magnitude of this, reminder, if you want the magnitude of the final velocity, it's going to be a square root of vfx squared plus vfy squared. If you want the angle, it's going to be tangent inverse of vfy over vfx. Though do note, if you all get the tangent inverse, so in this case you get lucky, it gives you a negative value, which denotes an angle below the horizontal. But that part I'll let you all do. That's just vector practice. That's not momentum practice. So there you go, y'all. Momentum. It's fairly straightforward. Add up your momentums at the beginning. They equal your momentums at the end. The only thing that makes it trickier is x and y. And I wouldn't use the word tricky. I would just say it's an extra step you got to do. All right. One more problem, and we've done all the types. So we've been building up. If you notice, we started with two objects in one dimension, doing an inelastic collision. Then we did two objects, doing an elastic collision. Then we did two objects, doing an inelastic collision in two dimensions. The last thing we're going to do is four objects, doing a separation. It's fine. All right, I got three deer. They're standing on a rock on an ice-covered pond. A gunshot goes off, the deer scatter. Deer A runs up and to the right. Deer B runs to the left and up. And deer C runs to the right and down. What is the velocity of the rock on which they're standing after they jump off? So it seems like a crazy problem, but momentum makes this problem really, really easy. That's the cool thing with this. You don't care the order that they jump off. You don't care how they jump off. You don't care anything. You just care about the beginning and the end. And we can figure out the velocity of the rock based on that. Draw a picture. First step. Can you draw a picture of this? If you cannot visualize what's going on in this problem, you're going to have a much harder time solving it. Also, it's good vector. Draw your arrows correctly. It's good practice in drawing vectors. Oh, and I hope this is obvious, but it will be obvious when you draw a picture. The J component here does not mean up and down. We're looking at it from above, y'all. We're not having these deer like crash into the ice. So like that's just an important thing. You can hopefully assume that this J is not like them flying up into the air or down into the earth. We're looking at it from above. The picture's from above. Again, if you're visualizing this problem, that should be very obvious. Otherwise, deer C literally like is plummeting headfirst into the ice at 45 miles per hour, which is not what's happening. So, all right. So here's my initial. I got a rock. We're going to make deer A purple. There's deer A. Here's deer B. It's orange. And here's deer C. There they are. Notice I didn't draw any velocity vectors because in the beginning they are sitting on a rock. Well, they're standing on a rock, but they're not moving. If you do not realize that they're not moving in the beginning, you cannot solve this problem. Our initial momentum is 0. If you do not realize that they're not moving in the beginning, the rest of the problem falls apart. Mm-hmm.
Since all three deer have the same mass,
Mm-hmm.
you think we should put M1A?
That's up to you. I'll kind of label it as that. But yeah, you can make your notation a little shorter here. But yeah, so the question was, since they all have the same mass, how do we kind of want to label that? Whatever makes the most sense to you. I'll show you how I'll label it. All right, so great. That's the beginning. And now we're going to practice drawing some vectors. So I'm going to draw deer A. So deer A is going to be purple, and this is great practice. Can you draw a vector correctly? 15 I hat plus 5 j hat. That means that's 15 to the right and 5 up. So that should be more right than up. The vector I drew here is approximate to this. 15 over, 5 up. For every 1 I go up, I need to go 3 over. All right. Deer B. And, it's not a disaster if you don't draw this picture right. But this is really good practice on drawing vectors. Negative 12 I hat plus 8 j hat. That is negative 12 to the left. And then that is 8 up. So negative 12. So deer B is over here. And they're going... It's not quite an 80 degree or a 45 degree angle. So something like this. Something kind of like that. Almost the same left and up, but not quite. And then deer C is going 1 to the right, 1.2 to the right, and 18 down. There we go. All right. I'm being accurate with my arrows just because this is good practice for you all. It is always good to practice these skills. You're going to draw a lot of vectors in your days ahead because you all have to take physics too. And you're going to draw more vectors. If you're a mechanical, aerospace, maybe electrical engineering, you're going to have to draw a lot more vectors than this. All right. Step 1. What's given? Mass A equals mass B equals mass C equals 70 kilograms. I'm going to make the executive decision and call the rock D, just so you know. Keep with the formatting. So mass D, if you want, you can call it mass rock. Do whatever you want. Notation is all just whatever helps you. We'll call it mass rock. I think that might make it easier when you look at this later. 200 kilograms, or you could call it mass D, or you could call it mass 4, whatever. I don't care. Okay, and now the initial velocity of A equals the initial velocity of B equals the initial velocity of C equals the initial velocity of D equals 0. And then the finals I'm going to immediately break up the finals, and I'm going to make a little table for this because I don't want to write as much. So I'm going to make a table because it's going to save me some writing. So V final A, V final B, V final D. Nope, there is no D. V final C. So dear A, this is 15, and this is 5. This is negative 12, and this is 8, and this is 1.2, and this is negative 18. I could have written that as 6 variables, but this saved me a tiny bit of writing, so I opted for it. And again, this problem seems way worse than it is. Like, we're spending a bunch of time on it because I'm being careful and I'm teaching you all it for the first time. But this problem really isn't that bad mathematically or setup-wise or anything like that. We're just being very thorough. All right, and we are finding the velocity of the rock final. Yep.
How can we find the final velocity of the rock? It doesn't move, does it?
It will move. It will move. We are on ice. If there was friction, the rock would not move. But for conservation momentum, there cannot be friction. Friction results in energy loss to the environment, and conservation momentum doesn't work if you're losing energy or gaining energy from the environment. So in this case, the rock will move, and that's because there's no friction. Yep, which is the only way you can do conservation momentum, is if we ignore friction or air resistance. That's a good question. Yep. No, you cannot do conservation of momentum. Yeah, so I think I have to kind of check on it. You would add an impulse to, I think, one side. So if you all remember, you have energy initial plus work equals energy final. In this case, you would have initial momentums, add them all up, plus impulse equals momentum final. But we're not going to bother with that in this class. Force times time. So I'd have to give you even more information. Yep. So yeah, that's a good thing. I'm just going to put it here real quick. Remember, this is the bread and butter of energy. Energy initial plus work equals energy final. There is one like this for momentum. The sum of momentum's initial plus the impulse equals the momentum final. Impulse was F times delta T. I'm not going to give you all any problems like that, but I just want to show you there's kind of an analogy. If there is a force acting on it, you can account for it with conservation momentum, but we're not going to bother with it in this problem. So, goodbye. All right. Great. Step 3. Build an equation. Sum of momentum's initial equals sum of momentum's final. You got to break it into X and Y. Do it to it. Build an equation, y'all. Build your own equation. Split it in X and Y. Don't forget. This one is the exact opposite of the last one. Well, this one they start together and they separate. The last one they started separate and they came together. So the setup for this will look very similar to the last problem we did, but opposite. Last problem, they started separated and they came together. This one they start together and they end up separated. It's a real squished rock. All right. 3 continued. So in the X direction, you have all of them together. MA plus MB plus MC plus MD times the velocity initial. equals MA V final X plus MB V final. Oh, goodness. Ugh, all the notations. VXA final XB plus MBV final XC plus M. Ugh, so easy to get these things mixed up. Mass rock V final X rock. It looks grosser than it is. It's just MV plus MV plus MV plus MV. They're all separated at the end, y'all. They're all free. In fact, in my picture, I guess I should have drawn this maybe a little different. In the final picture, this orange dot should be like off the rock. It's not on the rock anymore. So I'll redraw this very, very quickly. That deer is down that way. This deer is up that way. They have cleared the rock. Though, fun fact, they don't have to clear the rock for this to be true. If you all start running on an object, it will start sliding backwards on you. You know, think of a rug. That's why a rug slips out from underneath you. In some ways. All right. Let's set up the next equation, and I am not going to rewrite all that because that's too much. I'm going to copy and paste it. Ta-da! And then I just replace all these with y's. Turns out it's pretty easy to make an x into a y if you just don't care about how nice it looks. Ta-da! And then you just put in the numbers. Great news, the left side 0. That's nice. So I put all the things in there just for show you all the entire picture. This whole left side is 0 equals 70 times 15 plus 70 times negative 12 plus 70 times 1.2 plus 200 times V final rock in the x direction. Again, really straightforward. Yeah. Yeah, so the question was, can't you just find the magnitude of all the deer and not have to worry about x and y? Yes. If you only cared about the final velocity of the rock and you didn't care about the x and y, yes. What's cool about momentum is you can do everything together. So you could have found the magnitude of VFA, VFE, VFC, and you could actually do conservation momentum with the magnitudes, but it won't tell you the x and y components. So we get more information doing it this way. If we do it the other way, you lose that information. You will get how much the magnitude of the rock is, but you won't know which way it's going. And direction is very, very important if you want to get out of the way of the rock and things like that. So, great question, though. Conservation momentum, you can do it with the magnitudes. Totally valid. And you do some math, and you get the velocity of the rock, and the x direction is 0.21 meters per second. Ooh, be very, very careful. I made a mistake here. Negative. I forgot. Oh, also I typed in my calculator wrong. I made 2 mistakes. Gross. Divided by 200. 1.47. That answer's wrong. And it's negative. Do not put it as a positive. If you do, it's wrong. This is why y'all should always double check your work. Always check that when you plug. So this is my little spiel I get. The calculator is one of the best investments you all can make. because you're going to be using the same calculator for many years. This is a calculator from my high school. This calculator is from 14 years ago. I still use it. As long as you change batteries, it still works. I highly, highly, highly recommend you all have a calculator that lets you see what you typed in. The only reason I like using my graphing calculator versus the scientific one is when I type stuff in, it shows me it much nicer, and it's got a bigger window. I looked at this and I realized I accidentally multiplied two numbers. If your calculator does not let you see what you typed in previously, you will make silly mistakes, and it will be very hard to identify what the mistake is. So it's just one of those functional things. Your calculator is going to be your best friend for the next few years. Buy one that's nice. Go to Facebook Marketplace or something. They're not that expensive. I say that if you go to Facebook Marketplace, you can get like graphing ones. People sell them for like $30 or $40, which may be like, that's a lot of money. There's very few things in life you'll use for 14 years. Like, you're going to get a lot of mileage out of it, y'all. That's my pro tip to you. All right, now I have the pleasure of plugging in all the numbers here. 0 equals 70 times 5 plus 70 times 8 plus 70 times negative 18 plus 200 times V final Y rock. So 70 times, you can factor out the 70, which is nice. Saves you a little bit of plugging in. Positive 1.75. So the rock will move. And I'm going to double check it. I made a mistake last time. I don't want to make a mistake again. Yeah, it's good. All right. Rock will move. And which way will that rock move? If we call this rock red, it's going to move to the left and up. There you go. I mean, not that much. It's going to move. Yeah, barely. But it does move. So there you go, y'all. Conservation momentum. And what's really, this is a great example to show you all how powerful conservation momentum is. I didn't tell you which deer jumped off the rock first. I didn't tell you how they jumped off the rock. I didn't tell you if the deer slipped and fell on the rock and then got back up again and kept running. You don't care. It doesn't matter. It doesn't matter how these deer get off the rock. All that matters is when they get off the rock, they have this velocity. That's all you care about. You don't care the order. You don't care the time it takes. You don't care if they all get off at the same time or different times. And it just works. It just works. As long as there's no friction and air resistance. So, cool stuff. All right. Any final questions on momentum before we start gravity stuff? All right. Good stuff. Lots of fun. I will save my hard work. And I will upload these. Oop. Okay. All right. Now we're going to completely kind of switch gears. And we're going to enter into the last week of content that's going to show up on the test. So this upcoming test is energy, momentum, gravity, and center of mass. Energy and momentum are the main ones you need to focus on, but the last ones are important. All right. So the first chunk of this PowerPoint, I'm going to give you all a single equation. We're going to kind of discover it together. A single equation that explains why every single planetary body out there does what it does. The moon, the stars, every single planet, every single rock. A single equation is all you need to predict the motion of those things. Assuming none of them have a rocket attached to them. Which they don't. There's no asteroids with rockets attached to them. A single equation is all you need to predict the motion of every single planetary body out there. It's wild. All right. So, universal gravity. We're going to talk about it. We're going to talk about the guy that discovered it. We're going to talk about how he discovered it. We're going to kind of think through the logic a little bit together. All right. Centripetal force is the sum of all forces pointed inwards, outwards. You all need to remember this. It's going to come into play. Because most things that orbit make roughly a circular path. That's going to be helpful for us. Anytime things go in circle, somewhere in the back of your mind, you should have centripetal force, just kind of like in your back pocket. You might not use it, but it's a tool that's at your disposal if things go in a circle. And almost every planet roughly goes in a circle. Yes, some are elliptical orbits, but they're mostly all circular. That's called eccentricity. And you need to remember what mass is. Great. Okay. Hopefully this is not surprising to you that the force of gravity is m times g. On Earth's surface, this is true. We're going to say what happens when you leave Earth in any amount. And g is 9.8 on Earth's surface. We're going to derive that today. We're going to finally determine where that value, you can measure the gravity, but we're going to use the equation and show that it's also true. Great, nothing surprising here. Okay, now we get to discover the equation, the universal equation for gravity. We're going to kind of build it together. What happens to the force due to gravity as you get farther from the Earth? Does the force due to gravity go up, go down, or stay the same? Oh, I didn't. You have so much time to think about it. This means everyone's going to get the right answer, for sure. This is not a trick question, y'all. Go infinitely far away from the Earth and tell me what happens. All right, 10 more seconds. Go with your gut. And 5, 4, 3, 2, 1. Boop. Okay. Look, this is not a trick question, y'all. If you get infinitely far from the Earth, gravity gets weaker, right? Force due to gravity gets weaker. You get infinitely far from the Earth. Look, none of you all are worried about star Sagittarius out there and its gravitational effect on you. None of you are getting pulled towards the sun. Okay, technically you're getting pulled towards the sun. None of you are flying off the Earth right now because the sun is pulling you super strong. Gravity gets weaker as you get farther away. Great. They realized this back then. They realized that the sun was bigger than the Earth, and so it must get weaker as you get farther away, because otherwise the sun would win. Otherwise Jupiter would win. All right. So we've decided that as you get farther away, the force gets weaker. What magical quality does the Earth have that results in this force? Is it the magnetic field of the Earth? Is it the spin of the Earth? The fact that the Earth is spinning? Is it the fact that the Earth has mass? Or is it the fact that the Earth has water on it? Why are you stuck to this Earth? What magical quality does the Earth have that results in this? What makes the Earth different than other things? Well, okay, not different. That's not a great. Don't. I mean, in some ways, I guess you could argue it's unique, but that might have just resulted in a lot of people putting the wrong answer. We'll see. Go with your gut, y'all. All right. In 5, 4, 3, 2, 1. Okay, so why does Earth attract you all? Again, let's think through that logic that I just said. What is unique about the Earth? Yes, the Earth does have a magnetic field, but it's not that strong. If you put a magnet next to you, are any of you attracted to a magnet? No. If I put a magnet near you, a fridge magnet, which is way stronger than the Earth's magnetic field, none of you are immediately stuck to that magnet. It's not due to the magnetic field because, again, play with magnets, none of you get stuck to them. Is it because the Earth is spinning? No. In fact, spinning things, you should actually fly off of them. If you've ever ridden one of those rides that spin, you don't get attracted to the center. You want to fly off the thing and the walls keep you inside it. Hopefully it's obvious it's not water. The Earth is massive, like stupid massive. We're going to see in a future problem that this is the mass of the Earth. 5.97 times 10 to the 24 kilograms. I only know this number because I used it this morning. This number you can look at and say, yeah, that's a big number. But to really appreciate how big of a number this is, we're going to write it out. We're going to move that decimal place 24 times to the right because it's so easy to not realize how ridiculous this is. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Put some commas in there because did I mess up the commas? 1, 2, 3. Oh, man. All right. Thank you. 1, 2, 3, 1, 2, 3. My hand covers them. That's the excuse I'm using. That number is so stupid big. Here, let's put your mass next to it. Roughly, let's say the average human 70 kilograms. There you go. It's such a stupidly large number that, like, you can't even imagine it. The number of seconds that have happened. So, to give you a frame of reference for how big this is, let's look at how many seconds there have been in the universe since it was conceived to have started. So, whatever beliefs, all that kind of stuff, if you, based on whatever our best scientific understanding, they said the universe came into being a very, very long time ago. All you need to know is a stupid big number. Seconds since universe began. Again, people have different opinions about this, all that jazz. All right. Here's that number. Why am I getting two different answers? Nope, they're the same. All right. Let's put these numbers next to each other. So make this a little bit bigger so the scale matches. A little bit bigger. All right, this is how many seconds since the universe kind of began. The mass of the Earth is another billion or another million times more than that compared to a single kilogram. The reason I'm telling you all this is things in the solar system are so massive and so far apart, your brain cannot possibly comprehend how big they are or how far apart they are. And then you get into interesting questions about why is space so big? Why are planets so big? And that's a philosophy question. Fun one to think about. Why is the universe so big? Feel free to ask yourself that and ponder it. Stupid big number. All right. Okay. So, Isaac Newton proposed the idea that every object in the universe is affecting every object. Look, the Earth has a lot of mass, but it's not like when you reach a certain amount of mass, then gravity kicks in. It's not like there's a threshold at which point things exert gravity. Everything makes a gravitational field. Every single one of you is making a gravitational field that's attracting every single person in this room. Every single object with mass makes a gravitational field. You just need a lot of mass to actually feel it. So this is the thing he proposed, which is wild, because why would anyone come up with that idea 300 years ago? How do you come up with that idea? You look at the solar system and there's a lot of things orbiting a lot of things. You got planets and then you got moons orbiting those planets, and clearly, everything must be affecting each other. The sun is affecting the earth, and the earth is affecting the moon, and Jupiter is actually affecting the earth, and everything's affecting each other, and it's wild. And you got Saturn's rings, and Saturn's affecting all the little particles that make up its rings, and it's just crazy. Yeah. Oh, yeah. Gosh, I have no idea. They don't know. Yeah, the universe is expanding, which is wild. So according to this, you would think that the universe would collapse back on itself, but what's really wild is the universe is not only expanding, but it's actually expanding at a faster and faster rate. So things are not only getting farther from each other, they're getting faster away from each other, which is just weird, and they don't know why. Space-time is stretching, and why is that happening? Who knows? I think they probably have. I don't know for sure, but I would guess they have. That wouldn't be too hard to calculate. You would just look at an object, you would use a kinematics equation. You would just say, hey, how far away is it at this point? How far away is it at this point? You have the change in time, plug it into the kinematics equations. They can find that acceleration. All right. More concept questions. How does the force that you pull on the earth with compare to the force that the earth pulls on you with? Is the force of the earth on you greater than the force of you on earth? Is the force of earth on you less than the force of you on earth? Or are they the same? All right, give y'all 10 more seconds. And 5, 4, 3, 2, and 1. Boop. All right, Newton's third law, y'all. If I push on the earth with 5 newtons, how much does it push back? 5 newtons. Replace the word push with pull, and it works. Every single force has an equal and opposite. If the earth pulls on you with 100 newtons, you pull on the earth with 100 newtons. Now, there is the question, and there's a really good, there's a webcomic called XKCD, which you may or may not be familiar with, and they have a really fun book, they have a really fun thing that says what if, and they explore a lot of what if scenarios. Like, one of them that's really silly is, could you make a jetpack with, like, a gun? How many guns would you need to make a jetpack? And they do the math on it, it's really cool. One of the ones they do is they say, what if you took everyone on earth and you moved them into one location? What would that affect? And the answer is absolutely nothing. Why would it affect? And they even say, what if you jumped? But if you moved everyone on earth to one location, they both pull each other the same amount, nothing happens. You don't affect Earth's orbit because you're all stuck together. It's not going to change anything. Now, if you all jumped, it still doesn't matter, because if you add up the mass of everyone on Earth, it's nowhere close to the mass of the Earth. So conservation momentum, blah, blah, blah. All right, so we have decided 2 things. We have decided that mass matters. And as mass goes up, force goes up. We have also decided, so let's build our equation. Newton's third law, every force equal and opposite. That's what we just said. Let's build our gravity equation. We know mass matters. And we know as mass goes up, the force goes up. So I'm going to put mass in the numerator. As mass goes up, the force goes up. And you need 2 objects. You need 2 objects for there to be a force. Easy example. The earth is an object and you are an object. For you to experience gravity, the earth has to exist. Right? Like, you need 2 things. One makes a field, one experiences the field. You need 2 objects. And the order of operation on them is multiplication. 2 times 3 is the same as 3 times 2. Why? Newton's third law. The order doesn't matter. The force of 1 on 2 is the same as the force of 2 on 1. So we know it's multiplication. We know for sure it's multiplication. Now, one thing we don't know, what I'm writing down here is not the final equation. I want you all to note that. We are making the equation like Isaac Newton did a while back. There might be some exponent up here. There might be. I'm going to tell you there's not going to be. But there might be. He didn't know. He's discovering this equation for the first time. I could square both of these terms and the result is the same. So he's got to figure that out. And now we also decided, as you get farther from Earth, it gets weaker. So if my distance goes up, my force goes down. Which means, where do I need to put distance? On the bottom. We're going to use the variable r for distance. And again, he did not know. So we're building the equation. I will give you the final equation. So just note, this is not the final equation. We're building it like he did. We're building it like he did, and we'll call this letter K. Some exponent may or may not exist. He did not know whether or not this exponent existed. He had to discover it. How is he going to do that? He's going to do measurements. Now, here's the problem. They did not have accurate enough equipment back then to take two large objects and measure the force of gravity on them. Cavendish, 100 years later, did that experiment. He took two giant spheres with a lot of mass, and he brought them near each other, and he actually could measure the force of gravity on those two spheres. That was 100 years later, after Isaac Newton discovered this equation. So, Isaac Newton needed two really, really, really big objects. What are two really, really big objects that are convenient, that are as close to us as possible? The Earth and the Moon. That's the objects he looked at. He could find the acceleration due to gravity on Earth. But the question is, how do you find the acceleration due to gravity that the Moon experiences? The Moon's really far away. So we could figure out, the Moon is a certain distance away that they could find. They could figure out the acceleration and compare the two values. He did. He did measure how fast the Moon was going. That's really good. And we'll talk about really briefly how he did that. So, mass is required for the force. Greater the mass, greater the force. Two mass involved. Force on each is the same, so it doesn't matter. Look at that. So it's all the things we said. Oh, don't want to spoil it. Okay. So, how did Isaac Newton determine this equation that I'm about to show you? About to spoil it all. How did he figure this out? Well, he realized, and this is fairly obvious, it's going in a circle, right? So if you all remember, mv squared over r, the centripetal force, equals all the forces pointed inwards. The only force keeping the Moon attached to the Earth is gravity. So the centripetal force equals this equation. Again, he didn't know what these exponents were at this point. No idea. So we're just putting random exponents. We don't know what they are. And so what he was able to do, actually, let's kind of rewrite this a little bit differently. That's fine. One of these masses cancels. So this mass, and this is where it gets kind of weird, I guess. He did cancel that one. Let's look at it this way. Again, he didn't know those exponents. What he did know was this. He knew the centripetal acceleration. The acceleration that the Moon experienced due to the Earth could be found in this equation. What's cool here, the masses cancel. You don't need to know the mass of the Moon for this. And so what's the result of this? If you can figure out how far away the Moon is, and you can figure out how fast it's going, you can find the value of the acceleration that the Moon is experiencing. So on Earth, that acceleration is 9.8. We know that value. We can measure that. You drop some apples, measure the acceleration, easy peasy. So the question is, how did he find the velocity of the Moon? And this is the stuff where it's not impressive to discover stuff that someone else has already, okay, it can be impressive. It's not impressive to discover stuff with infinite resources. Like, nowadays, we can send sensors to the Moon and measure these things. Obviously, 300 years ago, they didn't have sensors on the Moon. So, like, how do you figure out, Spencer, how the heck do you figure out how fast the Moon's going 300 years ago? Like, think about that. See if y'all can come up with a strategy. It's a fun thought experiment. How do you do that using only the materials they had back then, which basically are telescopes? And, think about what they had. How the heck do you figure this out, y'all? What's really cool is the way he discovered is something you all can do nowadays. It's super, super easy. None of you need fancy equipment for this to work. He didn't have fancy equipment. Any ideas? Yeah. Ooh, so you could maybe. So how would you use the sundial? This is not how he did it, but I'm just curious.
Well, I guess you could like set your starting point at like some whatever like the angle of the shadow is.
Okay.
From the light from the moon, and then time it, and then measure the change in the angle of it, and then try to use that to find.
Okay, so maybe like during a solar eclipse or something. Yeah, maybe. I was like, you might be able to do a solar eclipse. Good news, you don't need a solar eclipse though, because it's actually kind of tricky to. I don't know if they could predict those super accurately back then. Maybe, may not have. I have no idea. They're not super common. Yeah, but a good idea.
Would you use like the stars, like since they pretty much map the stars, they would like go from one point and then you'll see where the moon goes?
Yeah, so you have stars that are super far away, and the stars can be effectively stationary. So if you all know, all you have to do is measure how long it takes the moon to pass in front of a star. If you measure how long it takes the moon to pass in front of a star, remember you all, x equals vt for a constant velocity. If you know how far, so you're solving for you're solving for v, x over t. So you can measure the time it takes for the moon to pass in front of a star and for the star to pop out the other side. Now, there is something you need here, which is how big the moon is. Great news, someone else did discover that for him way before that. He didn't have to discover how big the moon was. Someone else had actually figured that out, which is that's another wild. How the heck do you figure out how big the moon is without going to it and measuring it? Another really fun thing to figure out. Yeah.
Yeah, so since we were talking about, we were talking about that speed with like using that for speed, so you would take you would find you would find like how long it takes for the moon to like travel a certain orbit, and I know that the Greeks already calculate roughly the size of the Earth. So if you just extend that view to the trigonometric arc of the moon,
Yep.
also kind of equivalent, you can then measure across that angle, and then continue doing that for every angle that you observe it, and then sort of just literally integrate it, right?
Oh yeah, to figure out. So in this case, he literally just looked at some stars and just said how long does it take the moon to travel across that star. He treated the stars as stationary objects for this because they're so far away, and the moon's traveling so fast. And what's also really cool, they knew how far away the moon was at this point. Again, absolutely wild. How the heck do you figure out how far away the moon is? People did some clever stuff with Earth's shadow on the moon and did some relationships with geometry and things like that. Why am I spending so much time on this? You don't need to know anything I'm telling you. I'm spending the time on this because I want you all to appreciate that the discoveries that are made are not made with infinite resources. The people that are geniuses that discover these things are not geniuses because they have access to anything and everything. It's because they were clever. Genius is being clever. Anyone nowadays that you look at their genius, they are doing things that are clever, taking the existing resources and pushing beyond what people think are possible. 300 years ago, I would think it's impossible to figure out how big the moon is, and someone did it. 300 years, or even longer than that, they knew how big the moon was, I believe they knew the radius of the Earth in like a few hundred BC, which is absolutely wild. So, I encourage you all, if you ever think something's impossible, people have done many things that people thought were impossible using the existing resources that they had, and it's just an encouragement to you all. There's lots of things that are possible that don't seem possible, and you just got to come up with creative solutions. Those are the people that get paid the big bucks, that come up with solutions to seemingly impossible problems. All right, great. Long story short, he found the acceleration that the moon experienced. He did a ratio of the acceleration of the moon to the acceleration on Earth. And he found that it had a ratio of r squared. This is the final equation. The value of G was not discovered for 100 years after Newton. Cavendish discovered the value of G. But what he found is he compared the acceleration that the moon experienced to the acceleration on Earth. And when he compared those two values, he found that the ratio of the distances was the square of the distances. Cool stuff. So, yeah, feel free to kind of look into it more and kind of see how he discovered it if you're interested. But he did it for the ratio of the accelerations and the ratio of the distances. It's great. The value of capital G is 6.674 times 10 to the minus 11. That's a number. It's a gravitational constant. It will always be that number. Why does that number exist? Because the kilogram is made up. Meter is made up. Who decided a kilogram? It wasn't written in stone somewhere. All our units are made up numbers. They're just standardized. So this constant is kind of the thing that accounts for our random made up units. What is a kilogram? What is a meter? That was not written in stone somewhere and given to us by some external thing. We decided a kilogram is blank. It's arbitrary. All right. It's always towards each other. The unit is Newton because it's a force. And yeah, it's the masses are, there's no exponents for those. All right, we'll do a couple more problems on this. And then we'll call it good. I don't want to cram our heads with too many things. All right. Practice. Here's my equation. Force due to gravity is capital G, M1, M2 over R squared. What happens to that force if the distance between two objects doubles? I always like giving these problems. If this changes, then what happens? Oh, and I forgot to mention this. How did he figure out that there's no exponents to mass? Really, really simple. Just pick objects on Earth and measure how the force of gravity is different on them. If you double the mass, the force doubles. If you triple the mass, the force triples. You can test that on Earth. That was actually really easy to figure out. Distance was much harder. All right, give you 10 more seconds. In 5, 4, 3, 2, 1. All right, so this is my OG force. Right there, that's original. Nothing changed, that's what it is. My question is, what happens to it when I double it? So I make a new one. And in my new one, my mass is the same, and this is where you need to be careful. The distance is doubled, but whatever happens to distance, you need to square it. If you do not square it, you get the wrong answer. So we get G M1 M2 over 4R squared. Pull out the 4. And ta-da! It's 1/4 the original. Yay. Great job. Why did I ask this question? 1, get us used to this equation. 2, do not forget the square. Do not forget the square on the bottom. It's a classic mistake is forget the square at the bottom. Why? I don't know. It just happens. Classic. All right. I'm not going to worry about that one. Not going to worry about that one. Okay. I might reword this problem, and we'll do one last problem. What is the equation for the acceleration, the universal acceleration due to gravity? I don't know if I'm not going to make it a clicker question. I'm actually just going to make this a whole new thing. I want you all to derive this because it's so easy. Find the universal acceleration equation. You may be like, that's so much work. How can I do that? Oh my gosh. All right, here's force. Great, there it is. What does Newton's second law say? F equals. All right, solve for A. They both equal force. If that's the only force acting on something, solve for acceleration. I believe in you. So m times A equals g m1 m2 over r squared. There's two masses here because one makes a field, one experiences a field. This is something you're going to hear in physics too. Let's just say object 2 is the one that's Earth, and you're object 1, and I want to figure out the force on you. So we're going to call this m1. Oh my gosh, the m1 goes away. Ta-da! Chuck one of the m's out. There's the equation. Just get rid of an m. And the last thing I'll leave you all with is to finally connect how did Isaac Newton discover the r squared dependence. I kind of needed to get to this slide. The acceleration that the moon experienced and the acceleration on Earth equals the ratio of these two things. Oh, look, the m's cancel. Oh, look, g cancels. And that's how he discovered that it was an r squared relationship. It's cool. You don't need to know that, but that's how he did it. It's really, really cool. Just by watching the moon go in front of some stars and a bunch of other people before. All right, have fun, y'all. Next